Something happened to Voyager 1 that NASA has not fully explained. On February 27, 2026, during a routine maneuver 15 billion miles from Earth, this spacecraft, older than the internet, older than personal computers, running on less electricity than the bulb above your kitchen sink, experienced an unexpected power drop so severe that it nearly triggered an automatic self-shutdown sequence that engineers would have struggled to reverse. That alone is not the headline. The headline is what Voyager 1 has been transmitting from the darkness beyond our solar system before, during, and after that moment. Data that does not match what our best models said should be out there. And nobody is talking about it. There is a machine right now, at this exact moment, traveling through a region of the universe that no human eye has seen, no probe has mapped before it, and no scientific model has successfully described in advance. It is moving at 38,000 miles per hour. It has been moving continuously since 1977, and in the last few months of 2026, it has done something that should be stopping people in their tracks, something that should be dominating every science headline on the planet. Instead, the world is looking elsewhere, and that gap between what is happening out there and how little attention it is receiving is itself one of the most important things about this story. The machine is Voyager 1. You've probably heard the name, but what you have heard about it and what is actually happening with it right now are two very different things. Most people think of Voyager 1 as a feel-good story, a little spacecraft that kept going, a testament to human engineering, a golden record drifting through the dark. That version of the story is true, but it is incomplete. What is happening in 2026 is not a feel-good chapter. It is something significantly more complicated, more urgent, and more scientifically profound than the version of Voyager 1 most people carry around in their heads. And to understand what it just discovered, to understand why that discovery matters in a way that reaches far beyond the world of astrophysics, you need to first understand the precise situation this spacecraft is currently in, because the situation itself is extraordinary. As of March 2026, Voyager 1 is 172, 59 astronomical units from Earth. That number is almost impossible to hold in your mind as a real distance, so let us translate it. 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. Multiply that by 172. The resulting number, approximately 16 billion miles, is where Voyager 1 is right now. A signal traveling at the speed of light, the absolute speed limit of the universe, takes nearly 23. 5 hours just to reach it. If you send a command to Voyager 1 at noon today, it will not arrive until noon tomorrow. If the spacecraft responds immediately, you will not receive that response until noon the following day. Every single exchange between this spacecraft and the humans trying to operate it takes nearly 2 full days just for the round trip. Think about what that means for a moment in terms of real operational consequences. There's no quick fix available. There's no fast response possible. Every decision, every command, every attempt to diagnose a problem or adjust a system happens across a 44 to 47 hour communication loop using technology developed in the 1970s. And now here is where the situation becomes genuinely critical. On February 27, 2026, engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, were conducting what should have been a completely ordinary procedure. A scheduled roll maneuver, a routine recalibration of the spacecraft's magnetometer instrument, the kind of thing that gets done regularly and quietly without incident. Except this time, something went wrong. Voyager 1's power levels dropped unexpectedly during that maneuver, not by a catastrophic amount, not in a way that immediately destroyed anything, but the drop was significant enough to bring the spacecraft dangerously close to a threshold, a line in the power budget that, if crossed, would trigger an autonomous system aboard Voyager 1 called the Undervoltage Fault Protection Mechanism. This is the spacecraft's built-in emergency response. If power drops below a certain level, this system activates on its own without waiting for commands from Earth and begins shutting down components in whatever order its 1970s programming decides is safest. The resulting spacecraft state is not something engineers can quickly undo. Recovering from an undervoltage fault on a machine 16 billion miles away, communicating through a nearly 2-day round-trip signal delay, is a lengthy, complex, and extremely risky process. There is no guarantee of a successful recovery. The JPL team recognized immediately that if they did not act first, the spacecraft might act for them. And acting for them would almost certainly mean losing instruments, losing capabilities, possibly losing the mission entirely. So they did what this team has been doing for nearly 5 decades. They made a hard decision under impossible constraints, and they made it well. On April 17, 2026, mission engineers sent a sequence of commands on a 23-hour journey to Voyager 1, instructing it to shut down the low-energy charged particles experiment, the instrument known as the LECP. That command took 23 hours to arrive. The shutdown process itself, once the command was received, took an additional 3 hours and 15 minutes to complete. an instrument that had been operating almost without interruption for 49 years, since Voyager 1 left the launch pad at Kennedy Space Center in September 1977, went dark. Not because it had failed, not because it was broken, but because the spacecraft simply does not have enough electricity left to keep it running safely alongside everything else that still needs power to keep Voyager 1 alive and transmitting. That distinction matters enormously. The LECP was not lost, it was sacrificed. There's a profound difference between those two things. The people who made that decision understood exactly what they were giving up. What the LECP had been doing for those 49 years was not trivial. It measured low-energy charged particles, ions, electrons, and cosmic rays coming from both our solar system and the broader galaxy beyond it. In the years since Voyager 1 crossed into true interstellar space in 2012, the LECP had been delivering something unprecedented: direct measurements of the particle environment in the space between stars. Scientists studying the interstellar medium, the plasma and magnetic fields and charged particles that fill the vast distances between stellar systems, had been using LECP data to understand pressure fronts, density variations, regions where particle concentrations shift in ways that no Earth-based observation or theoretical model had predicted. This was not background data. This was irreplaceable frontline science from a region of the universe no other instrument has ever physically been inside. And now that instrument is off, the data stream it provided has ended. That stream cannot be replaced because there is nothing else out there. Voyager 1 is alone in interstellar space, and it is now running on 2 instruments instead of 3. Those 2 remaining instruments are the plasma wave subsystem and the magnetometer. According to Kareem Badruddin, the Voyager mission manager at JPL, both instruments are still working well, still returning data from a region of space no other human-made object has ever explored. But the margin for error around keeping those 2 instruments operational is now razor thin. Voyager 1's power is generated by 3 radioisotope thermoelectric generators, devices that convert heat from the radioactive decay of plutonium-238 into electricity. At launch in 1977, those generators produced approximately 470 watts of power. Every year, as the plutonium decays, the generators produce about 4 fewer watts. After nearly 49 years, the power budget has shrunk dramatically. The spacecraft is now operating on what engineers describe as critically limited power. The number being cited in recent reports is approximately 22 watts of total electrical output, less than the light above your kitchen sink. And that 22 watts has to run everything: the communication systems, the attitude control systems, the heaters that keep the fuel lines from freezing in the minus 270 degrees Celsius ambient temperature of interstellar space, and whatever science instruments remain active. Every watt matters. Every decision about where that power goes is a trade-off with permanent consequences. The temperature issue deserves a moment of attention because it illustrates just how precisely balanced this spacecraft's survival has become. Voyager 1 contains fuel lines, electronics, and mechanical components that must be kept above a minimum temperature to function. The environment surrounding the spacecraft is almost unimaginably cold. If a heater is turned off to save power, the component it was protecting begins to cool. If it gets cold enough, it could freeze, crack, or fail entirely. And any component that fails on Voyager 1 fails permanently because there is no repair crew available in interstellar space. The engineers at JPL are managing a system where turning off one thing to save power might mean losing another thing to cold, and losing that other thing might mean losing the mission months or years earlier than the power budget alone would have dictated. Every choice is a calculation across multiple failure modes, performed across a 44-hour communication delay, using programming languages and hardware architectures that were state-of-the-art, in a decade when most of the people making those choices had not yet been born. And this is where everything changes in 2026, because the JPL team is not simply trying to extend Voyager 1's life passively. They have developed something ambitious, something that has no precedent in the history of deep space operations. They are calling it, internally, the Big Bang. That name is not chosen lightly. The Big Bang procedure is a coordinated overhaul of how power is distributed across Voyager 1's electrical system. It involves switching off a group of powered devices simultaneously and replacing them with low-power alternatives, essentially restructuring the spacecraft's internal power architecture from 16 billion miles away, using nothing but radio signals and engineering expertise accumulated over 5 decades of working with this specific machine. The goal is to free up enough additional power that Voyager 1 can continue operating its 2 remaining science instruments for longer than current projections allow, and potentially even restore power to the LECP that was shut down in April. That last possibility, bringing the LECP back online after deactivating it, is not something the team is optimistic about. But they are not ruling it out either, because the Big Bang procedure is risky because it involves simultaneous changes to multiple systems on a spacecraft with no redundancy and no margin for error. The team is not attempting it on Voyager 1 first. Instead, they are using Voyager 2 as the test case. Voyager 2, Voyager 1's twin probe, also launched in 1977, is currently about 13 billion miles from Earth, slightly closer and with slightly more available power. Tests on Voyager 2 are scheduled for May and June 2026. If those tests succeed, if the Big Bang works on Voyager 2 without triggering any unexpected failures or cascading shutdowns, then the same procedure will be attempted on Voyager 1 no earlier than July 2026. If the Big Bang succeeds on both spacecraft, NASA engineers believe there is a real possibility of keeping at least one science instrument operational on each probe into the early 2030s. If it fails, the timeline contracts sharply. The window during which Voyager 1 can return meaningful scientific data from interstellar space becomes significantly shorter. But here is what most people are not seeing when they read about the LECP shutdown or the Big Bang procedure. The engineering story, extraordinary as it is not actually the most important thing happening here. The most important thing is what Voyager 1 has been finding out there, what it has been sending back. What that data is revealing about the nature of interstellar space, and what those revelations mean for our understanding of the environment in which our entire solar system exists. Because the picture that Voyager 1's instruments have been building since 2012, and that the plasma wave subsystem and magnetometer are still building right now in 2026, is a picture of the universe that does not match what the textbooks described. Not in minor ways, in fundamental ways, in ways that require the models to be revised, the assumptions to be revisited, and the conclusions to be drawn with far more uncertainty than the scientific community was previously working with. When Voyager 1 crossed the heliopause in August 2012, it became the first human-made object to enter interstellar space. The heliopause is the boundary where the solar wind, the constant stream of charged particles flowing outward from the sun and surrounding everything we call our solar system, finally loses the battle against the pressure of the interstellar medium and stops. Beyond that boundary, there is no more solar wind. There is no more solar influence in any meaningful physical sense. There is only the ancient plasma of interstellar space, filled with particles from stars that lived and died billions of years before our sun was born. Scientists had been theorizing about what that crossing would look like for decades. They had built models, run simulations, constructed theoretical frameworks about what Voyager 1 would find when it finally reached that boundary. The models were not entirely wrong, but they were wrong about the things that turned out to matter most. What the models predicted at the heliopause was a relatively gradual transition, a slow fading of solar influence, a reasonably well-defined boundary between the hot solar plasma inside and the cooler interstellar plasma outside, a clear shift in the magnetic field environment. What Voyager 1 actually measured was something dramatically different from that picture. The boundary region was hot, extraordinarily hot. Particles at the heliopause were moving at energies approaching a significant fraction of the speed of light, colliding and interacting in what should have been a sparse, low-density transitional zone, producing temperatures approaching 54,000 degrees Fahrenheit in a region of space that was supposed to be relatively cold by stellar standards. Scientists have described this region, the compressed boundary where solar wind meets interstellar plasma, as a wall of fire. Not fire in any combustion sense, but an intensely energetic concentration of charged particles, creating a cosmic heat signature at the very frontier of our solar neighborhood. Nothing in the theoretical models had predicted that level of energetic activity at the boundary. Nothing in the simulations had suggested that the transition zone would be that hot, that dynamic, that physically extreme. And then there was the magnetic field discovery. For decades, one of the most confident predictions about what would happen when a spacecraft crossed the heliopause was that the magnetic field environment would change dramatically. Inside the heliosphere, the magnetic field is dominated by the sun's field, stretched and shaped by the solar wind as it flows outward. Outside the heliopause, the galactic magnetic field of interstellar space was expected to take over completely, oriented differently, behaving differently, representing a clean transition from one magnetic environment to another. What Voyager 1's magnetometer found was that the two environments were not cleanly separated in the way the models had predicted. The magnetic fields inside the heliopause and those in the interstellar space immediately beyond it were surprisingly similar in their orientation and behavior. The sun's magnetic field lines, dragged outward by the solar wind and compressed against the heliopause boundary, were found to be connecting with and interacting with the galactic magnetic field in a process called magnetic reconnection, where field lines from different environments rearrange themselves and release significant amounts of energy in the process. This was not in the models. This was not expected. And its implications extend far beyond the immediate boundary region. What magnetic reconnection at the heliopause means, what it actually implies for the bigger picture, is that our solar system is not the sealed bubble that decades of theoretical models described. The heliosphere does not simply contain the sun's magnetic influence and block the galaxy's influence from reaching inward. The two environments interact. They are physically connected at the boundary in ways that allow energy to transfer between them, in ways that mean what happens in interstellar space is not entirely disconnected from what happens inside our solar system. The solar system is not an island drifting through an indifferent void. It is an active participant in a galactic magnetic environment that pushes back, that has its own structure and personality, and that is connected to everything inside the heliopause in ways that are still being worked out. And the only instrument physically present at and beyond that boundary, the only instrument giving us real-time data about how that connection actually works, is Voyager 1. The plasma wave subsystem, the instrument that is still operating on Voyager 1 as of mid-2026, has been detecting something in the interstellar medium that the scientific community has been studying carefully and cannot yet fully explain. Since 2017, it has been picking up a persistent narrowband emission, a faint but continuous hum in the plasma of interstellar space, present year after year across a vast stretch of the interstellar medium as Voyager 1 moves through it. This is not a single anomalous reading that could be attributed to instrument error or a temporary space weather event. It is a continuous signal that has persisted across more than a decade of observations and across an enormous volume of interstellar space. What this emission is telling scientists, according to peer-reviewed research, is that the interstellar medium is not the quiet, uniform, relatively featureless void that earlier models described. It is turbulent. It has structure at every scale, from the very small to the astronomically large. It has density fluctuations and plasma oscillations that create a kind of weather, a dynamic, shifting environment that influences the boundary of our solar system and everything behind it. The real scientific debate right now is about the nature of that persistent emission. Researchers have identified two possible explanations. The first is that the signal is caused by thermally excited plasma oscillations, the natural vibration of plasma particles as they interact with their thermal environment. This would be significant as a measurement, but it would fit within existing theoretical frameworks. The second possibility is a phenomenon called quasi-thermal noise, which arises from the random thermal motion of electrons in a plasma and carries information about plasma density and temperature in a subtly but importantly different way. Distinguishing between these two mechanisms requires either significantly more data from Voyager 1 itself, or a future interstellar mission equipped with instruments designed specifically to make this determination. There is currently no such mission. There is currently no funded successor to Voyager 1 in the mission pipeline, which means the answer to this specific scientific question about the fundamental nature of what is generating that persistent plasma emission in interstellar space depends in part on how much longer Voyager 1 can keep its plasma wave subsystem running. Every additional month of data from that instrument is a month closer to an answer that cannot be obtained any other way. What the plasma wave subsystem has already provided, regardless of which explanation for the persistent emission turns out to be correct, is something that has never existed before in the history of science: a continuous, ongoing measurement of interstellar plasma density. Previously, scientists studying the interstellar medium had access only to point measurements, isolated snapshots of plasma conditions triggered by specific events like shocks from solar coronal mass ejections crossing the heliopause. Those measurements were valuable, but they were scattered and event-dependent. They were like trying to understand the climate of an entire continent by checking the temperature in one city once or twice a year. What Voyager 1's plasma wave subsystem is providing instead is a living, ongoing portrait of the interstellar medium as the spacecraft moves through it. A weather map, not a snapshot, a continuous readout of a dynamic environment rather than isolated points of data in an otherwise blank record. And what that portrait is showing is an interstellar medium that is far more complex, far more variable, and far more structured than anyone had assumed it would be before we had an instrument inside it. This has direct consequences that do not stay neatly confined to the field of interstellar physics. They come back to us. If the interstellar medium surrounding our solar system is more turbulent and more structured than the models predicted, then the heliopause, the boundary that separates it from our solar system, is also more dynamic and more variable than we assumed. And if the heliopause is more variable, then the heliosphere itself, the bubble of solar wind and solar magnetic field that surrounds all 8 planets, all the asteroids, all the comets, and every living thing on Earth, is being influenced by a more complex external environment than we had accounted for. The heliosphere is the shield that protects life on Earth from the full intensity of cosmic radiation from the galaxy. If that shield is responding to a more turbulent external environment in ways our models did not predict, then understanding the true nature of that external environment, the interstellar medium itself, is not purely academic. It has implications for understanding the long-term conditions for life on Earth, and for understanding what future human missions venturing beyond the inner solar system will actually encounter. Now consider what is happening in November 2026, because there is a milestone approaching that has never been reached before in human history. On November 18th, 2026, at 2:16 in the morning Pacific Standard Time, Voyager 1 will be exactly one light day from Earth. That means the spacecraft will be 94 billion miles away. So far that a signal moving at the speed of light takes a full 24 hours just to reach it. This is not a record in any simple statistics book sense. This is a threshold that redefines the operational reality of communicating with this spacecraft. If you send a command to Voyager 1, Voyager 1 at 8 in the morning on a Monday, the spacecraft will not receive it until 8 in the morning on Tuesday. If it responds immediately, you will not receive the response until 8 in the morning on Wednesday. The communication delay is no longer measured in hours, it is measured in days. And it will keep growing because Voyager 1's one is still accelerating relative to the expansion of the space it is moving through, and there's nothing out there to slow it down. The laws of physics will not allow a deceleration that was never engineered into the spacecraft's design. It goes where momentum and gravity have already decided it is going, and it has been going there for 49 years without pause. Between May 2025 and February 2026, there was an additional complication that illustrates just how fragile the connection to Voyager 1 has become. Deep Space Station 43, located in Canberra, Australia, and the only antenna on Earth capable of sending commands to Voyager 1 and Voyager 2, was taken offline for major upgrades. For approximately 9 months, the JPL team had only limited operational windows in August and December 2025, during which they could actually send commands to either spacecraft. This created a critical deadline. Engineers needed to revive the backup roll thrusters on Voyager 1 before the antenna went fully offline, because losing the ability to control the spacecraft's orientation, to keep its antenna pointed at Earth, would effectively end the mission regardless of how much power the spacecraft had left. They succeeded. In May 2025, the backup roll thrusters that had been unusable since 2004 were successfully revived. But the episode serves as a reminder that Voyager 1's connection to Earth is not just limited by power and distance, it is limited by the availability of very specific, irreplaceable infrastructure on this end of the link, infrastructure that itself requires maintenance and periodic upgrades. Susie Dodd, the Voyager project manager at JPL, has described the goal for the coming years with striking clarity. The team wants to keep the plasma wave subsystem and the magnetometer running on both Voyager spacecraft, functioning essentially as weather satellites in interstellar space, providing a continuous real-time readout of the environment they are moving through. The scientific value of that readout, of that ongoing portrait of interstellar conditions, is something that cannot be replicated by any existing or near-term planned mission. If the Big Bang procedure works as hoped and the power budget can be extended even partially, the current projection is that at least one science instrument on each spacecraft could keep returning data into the early 2030s. If the RTGs continue declining at their current rate without the benefit of the Big Bang optimization, the timeline is shorter. The RTGs are theoretically capable of providing enough power for engineering data, if not science data, until approximately 2036. But the science instruments require more power than the engineering systems alone. The window for science is narrower than the window for the spacecraft's basic survival. And when that science window finally closes, something genuinely irreplaceable will end. Not just a mission, not just a program, a perspective. Voyager 1 is not simply a data source. It is the only instrument humanity has ever placed in interstellar space, the only physical presence we have ever had in the environment beyond our solar system. Every piece of data it has ever returned, from the first Jupiter flyby images in 1979 to the persistent plasma wave emissions it is detecting right now in 2026, has come from a vantage point that no human-built instrument will occupy again for a very long time. If a successor mission were funded and launched today, it would take at minimum 25 years to reach the heliopause, more likely longer, depending on the trajectory and propulsion technology available, which means there's a gap coming, a silence, a period of somewhere between 3 and 5 decades, during which humanity will have no instrument in interstellar space, no real-time measurement of the interstellar medium, no physical presence at or beyond the boundary of our solar system. And during that silence, the questions that Voyager 1 has raised will sit unanswered. The mechanisms behind the persistent plasma emission, the true three-dimensional structure of the interstellar medium, the precise dynamics of magnetic reconnection at the heliopause, the question of whether the conditions Voyager 1 has measured are typical of the interstellar medium throughout the galaxy, or specific to the particular region our solar system happens to be passing through right now. None of these questions can be answered from here. They can only be answered by something that is out there. And right now, the only thing out there is Voyager 1, running on 22 watts, down to 2 instruments, approaching a communication delay measured in full calendar days, being kept alive by a team of engineers that includes retired NASA scientists in their 80s and mission specialists so young that their parents were not alive when Voyager 1 was built. This is what is actually happening. This is the real story behind the headlines about power shutdowns and instrument deactivations. Not the slow death of an old machine, but the final urgent transmission of the only witness humanity has ever placed in the space between stars. The plasma wave subsystem is still listening, the magnetometer is still measuring, the data is still traveling for nearly 24 hours across the void to reach the antennas waiting for it on Earth. And what that data is saying, when you translate it out of the language of plasma frequencies and magnetic field vectors, is something that should command the full attention of every person on this planet who has ever looked up at the night sky and wondered what is actually out there beyond the light. What Voyager 1 is telling us is that the space between stars is not empty. It is not quiet. It is not the peaceful void of science fiction or the featureless background of older theoretical models. It is a roiling, dynamic, magnetically complex environment with structure and turbulence at every scale, an environment that is actively interacting with the boundary of our solar system in ways our models did not predict and that we do not yet fully understand. And the shield that separates us from that environment, the heliosphere that makes life on Earth possible, is responding to that complexity in ways we are only now beginning to measure. That is not a comforting message. It was never going to be. The universe has a consistent history of being larger, stranger, and more indifferent to human comfort than we are capable of imagining from inside it. Voyager 1 is the proof of that. And for this one brief, extraordinary, rapidly closing window in the history of human civilization, it is still out there, still transmitting, still telling us things we do not know. The question is not whether the data is important. The question is whether we are paying close enough attention to hear what it is actually saying before the signal finally fades.